An entity is simply a thing we care about, like a student, a car, or a pet. An entity set is the whole collection of those things. In math, we write a set with curly braces. Student equals open curly brace S1, S2, S3, and so on, close curly brace. Each element S1, S2, and so on is an entity. To tell one entity apart from another, we give it a special label called an identifier or primary key. For students, we might use a student number, so the identifier function looks like ID of S equals 20231001. Formally, an entity set E is a pair E and ID, where E is a non-empty set of entities, and ID maps from E to the natural numbers and is injective, meaning different entities get different numbers. This is the formal notation that ER diagrams hide behind the picture of a rectangle labeled student. Attributes are the pieces of information we store about an entity. Simple attribute holds one atomic value. Example, age of S belongs to natural numbers. If Alice is 12, age of Alice equals 12. Composite attribute can be broken into smaller simple parts. Example, address of S equals street city zip. Address maps student to street times city times zip. If Bob lives at 5 Oak Street, London, 12345, then address of Bob equals 5 Oak Street, London, 12345. Multi-valued attribute an entity may have many values of the same kind. Example, phone of S is a subset of phone numbers. Phone of Carol equals 5551010 and 5552020. Formally, phone maps student to power set of string, where power set is the set of all subsets. Derived attribute value computed from other attributes. Example, age of S equals today minus birth date of S. Age of Dave equals 2026-02-18 minus 2000-05-10 equals 25 years approximately. Derived attributes are usually shown with a dotted oval in ER diagrams because they are not stored directly. They are calculated when needed. A key attribute, or simply key, is a set of attributes that can uniquely identify every entity in an entity set. A candidate key is any minimal set of attributes with this uniqueness property. Uniqueness, for a key K, if two entities E1 and E2 have the same K value, then they must be the same entity. For all E1, E2, and E, K of E1 equals K of E2 implies E1 equals E2. Minimality, no proper subset of K still has the uniqueness property. Formally, if K equals set A and B is a candidate key, then neither A nor B alone is a key. Proof sketch, assume K is a candidate key. Suppose a proper subset S is less than K were also unique. Then K would not be minimal because S would be a smaller key, contradicting the definition. Hence, every candidate key must be minimal. In practice, we often pick one candidate key as the primary key, the one the DBMS will enforce with a special index. For a student entity, student ID is a candidate key. Email might also be a candidate key if every student has a unique email address. Explanation: each attribute has a domain dash the set of all legal values it may hold. The domain is a logical concept. The DBMS maps it to a data type that tells the computer how to store the value. Integer example values 0, 1, 42. Physical data types int and smallint. Typical storage 4 bytes. Fixed length text example value AB12. Physical data type char4. Typical storage 4 bytes. Variable length text example value Alice. Physical data type varchar50. Typical storage 1 byte length plus characters. Date example value 2026-02-18. Physical data type date. Typical storage 3 bytes for year month day. Boolean true or false. Physical data type bit. Typical storage 1 bit packed. The mapping decides how much space is used and what operations are fast. For instance, an int can store values from -2,147,483,648 to 2,147,483,647. So the domain of an attribute defined as int is that numeric interval. When we design an ER model, we first choose the logical domain, for example, non-negative integer, and later the DBMS chooses a physical type, for example, unsigned int. This two-step view keeps the model independent of any particular storage technology. A null value means we don't know or the value does not exist. It is different from an empty string or the number 0. Those are actual known values. Optional attribute. If an attribute may be missing for some entities, we allow nulls. For example, middle name for a person. Some people have no middle name, so middle name of John equals null. Semantics SQL uses 3-valued logic: true, false, unknown. Compare null equals null gives unknown, not true. This affects where clauses, check constraints, and joins. Integrity implications. A not null constraint forces every row to have a real value, guaranteeing completeness for that attribute. A unique constraint treats multiple nulls as non-conflicting. Most database management systems allow several rows with null in a unique column because null is not equal to null. Understanding nulls helps avoid bugs like missing data disappears from reports or duplicate rows appear, because nulls bypass uniqueness checks. Good naming makes a model readable for humans and machines. Conventions. Snake case first underscore name or camel case first name dash pick one style and stay consistent. Use singular nouns for attribute names, age, salary, because each value belongs to one entity. Avoid reserved words, date, order, or prefix them, order underscore date. Include the source or unit if it helps, price underscore USD, height underscore cm. Documentation. For every attribute, write a short description, its domain, whether it can be null, and any business rules. Store this in a data dictionary table or a separate markdown file. Example entry. Attribute : birth underscore date, entity : person, domain : date, open parenthesis 1900-1-1 to today close parenthesis. Null ? Not null. Description : the day the person was born, used to compute age. Clear docs let developers, analysts, and future designers all speak the same language. Explanation. Turning an ER diagram into a relational schema is like turning a picture into a LEGO construction plan. 1. Entity maps to table, each rectangle becomes a table. Example: student maps to table student. 2. Attribute maps to column. Every attribute becomes a column inside that table. 3. Key attribute maps to primary key column. The identifiers become the primary key of the table. Example conversion. Entity student, attribute student ID key, first name, last name, birth date, email. Relational schema SQL. Create table student. Student ID integer not null, first name varchar 30 not null, last name varchar 30 not null, birth date date not null, email varchar 50 not null, primary key student ID. If an entity has a multi-valued attribute, we usually create a separate table to hold the repeating values linked by a foreign key. Thus, the ER model gives a high-level view. The relational schema is the exact set of tables, columns, and keys the DBMS will store. Integrity constraints are rules that keep the data trustworthy. Entity integrity: every table's primary key must be not null and unique. No two rows can have the same primary key value. Domain constraints: each column must contain values only from its defined domain. For example, age must be an integer between 0 and 150. In SQL, we enforce this with column data types and check clauses. Check age between 0 and 150. Check constraints: custom rules that involve one or more columns. Example for a salary column that cannot be negative. Check salary greater than or equal to 0. Or a rule that a start date must be earlier than an end date in a project table. Check start date less than end date. These constraints are stored in the database schema and are automatically evaluated whenever rows are inserted or updated, preventing accidental bad data from entering the system. Explanation: let's walk through a simple real-world case, a library that lends books to members. 1. Identify nouns in the story book member loan. 2. Make entities. Each noun becomes an entity set. Book with attributes ISBN key, title, author, publication year. Member with attributes member ID key, first name, last name, join date. Loan with attributes loan ID key, loan date, return date, derived days overdue. 3. Identify relationships. A member can borrow many books. A book can be borrowed many times. Relationship borrows between member and book with cardinality. Member one to many, loan many to one, book one to many. 4. Add foreign keys in the relational mapping. Table loan gets member ID and ISBN as foreign keys linking to member and book. 5. Define constraints. Loan date cannot be null. Return date can be null because the book may not yet be returned. Check that return date is null or return date is greater than or equal to loan date. 6. Document each attribute. For example, ISBN is a 13-digit string, cannot be null and must be unique. 7. Create tables. Create table book with columns ISBN char 13 primary key, title variable character 100 not null, author variable character 60 not null, publication year small integer not null. Create table member with columns member ID integer primary key, first name variable character 30 not null, last name variable character 30 not null, join date date not null. Create table loan with columns loan ID integer primary key, member ID integer not null, ISBN char 13 not null, loan date date not null, return date date nullable, foreign key member ID references member ID, foreign key ISBN references book ISBN, and a check that return date is null or return date is greater than or equal to loan date.